Hello, yes, I've done previous videos on telescopes and on telescope mounts, so it's about time I did one on eyepieces because that's the third major part of a telescope setup that you'll encounter when you get into astronomy, if you do. Now, most astronomical telescopes, and by most I mean the vast majority, so usually anything apart from the cheapest ones, they allow for changeable eyepieces. And this is something that people are often not familiar with because they might have used other telescopes or even binoculars, which, when they're used terrestrially, they don't have usually changeable eyepieces. I mean, some of them do, but quite often they don't. So, yeah, when it comes to astronomical observing, there's a real range of objects that we'll want to look at. So some of them we can increase to quite high magnification, usually because they've got a lot of light coming from them, such as the moon or the brighter planets and such like. So we can magnify those objects a lot and have a lot of light to spread around, essentially. You need to have a lot of light from an object if you're going to magnify it a lot. So we can use eyepieces with a short focal length, maybe say 5 millimeters, something like that, and that's going to give us some quite high magnification. Or you might be looking at a galaxy or a nebula or something like that, where you don't have as much light and they're spread over a very large area. So we can't have too much magnification because we haven't got much light to spread out, and we need to fit it into our field of view. So you might have I don't know, like a 40 millimeter focal length eyepiece, something like that. Maybe even longer, depending on what it is that you're looking at and what you're trying to achieve. And you can easily change these in and out from the tube of the telescope. So you just get, where you're looking into the telescope, you'll have a barrel which will typically be 1¼ inches in diameter, and there's a little knob on the side which that's a sort of tightening knob for screwing. You push the eyepiece in and then you just tighten the knob round and it just holds it in place. You want to change the eyepiece, you just loosen it, take it out and put the next one in. So it's very easy to just flick around from one to the other. And of course, you're still going to have the focusing mechanism for this. So there'll be, another knob on the side, which you can then rotate round, which will drive the eyepiece in or out of the telescope tube, because we need to get the focal plane of the eyepiece and the focal plane of the telescope lined up. So if you had a refracting telescope and the light's coming in this end and say it was focusing down to some point, I'd say this was the focal plane of the telescope, and then you stick an eyepiece in the end, you plug it in here, and you need to move this eyepiece in and out of the tube until the focal plane of the eyepiece is in the same place, and then we're going to have a sharp image. So that's what we're doing with that focuser, and that's exactly the same as you get on other telescopes, terrestrial telescopes, binoculars, things like that. So there's no difference there. The only difference here is more common to change the eyepieces around. I mean, you also get things like filters. If you want to look at a particular wavelength of light and such like, then you can screw the filter into the end of the eyepiece. So the eyepiece normally you'll get a black bit with a slightly narrower metal bit at one end. Is the metal bit that you're sliding into the barrel here that goes into the telescope. So that's why it's a little bit narrower. You push that narrower bit in and then tighten this knob up against it. But at the end, these have got screw threads on the inside. So you can screw in these narrow, they're not very wide, the filters. You just screw them in. And it might be, okay, well, I'm going to look at this in red light. Or if you're looking at, like something like the Ring Nebula, say, you might want to put in an O3 filter. So that's looking at a particular emission line of oxygen, which is a large part of the light that's being emitted. So it helps filter out a lot of the rubbish around that you're not interested in, and just trying to get the light that's specifically coming from a particular object. So you can put filters on these eyepieces as well, but I'm not really focusing on filters in this video. So yeah, you can put these in, you can do the focus in. So what are the differences? Because there's a big range in prices in eyepieces. You can buy some eyepieces that might be, 20 or 30 quid. You might even be able to, get a whole set of eyepieces of all the different focal lengths that by and large you're going to need as a beginner astronomer, and you might pay out £100 or something like that. But then you'll have other people who'll be paying out £500 just for one eyepiece. So what is going on? Why is someone wanting to pay out so much money for one eyepiece? So first thing, chromatic aberration. Now I mentioned this in the aberration video that I did previously. So this is where you're getting different wavelengths of light refracting by different amounts, so focusing in different places. Now this can be corrected for in eyepieces quite often by having these compound lenses. So you can get, you might get a doublet like this. Doublet is in, we've got two lenses that have been either very well engineered and placed together or actually stuck together. Now these lenses they'll often have this format that you'll get this this convex, double convex lens and then a plano concave lens going next to it. And this will reduce the effects of chromatic aberration. So you're getting this sort of refract inwards and then outwards effect. And that, once done over all wavelengths, it greatly reduces the effects of chromatic aberration. These will often be made of two different types of glass. So you might get crown glass on one of them and flint glass on the other, say. So crown glass has got a relatively low refractive index. So it's got low dispersion, as it's not creating a huge difference in refraction depending on wavelength. So it's got low dispersion and relatively low refractive index. Flint glass is, well, the opposite really. It's got higher dispersion and a relatively high refractive index for glass. So I mean, they're called crown glass. This was because crown glass was first made in France, I think, and they used to spin it. So you're spinning this glass round to try and make it flat, but you'd end up getting a sheet with a bulge in the middle, and you couldn't use the bulge, and it looked like you had a crown in the middle, so it got named after that. Flint glass, that is from deposit. So this was first made in southeast England, I think. Flint glass. Oh, I don't think I've just appropriated that for England, or at least that's where it would have got the name from, I think, of flint glass, because there were a lot of flint deposits in southeast England. There was more flint, less calcium. And this is the precursor to lead crystal, like the fancy glasses that you can get, as in drinking glasses. So, yeah, you get these two different types of glass, and the difference in dispersal and refractive index means you're reducing chromatic aberration. So you've got a number of issues, as I'm sure you can immediately see here if you're going to manufacture one of these. You've got the engineering of getting them to fit together nicely. You've got the engineering of cancelling the chromatic aberration. You've got are they stuck together or held together? You've got the different types of glass. So the more elements you've got in an eyepiece, the more it's going to cost. And it also brings on the next issue of internal reflection or scatter, because every time you've got a boundary, then you've got some reflection going on. So the more elements that you put into an eyepiece in order to reduce the effects of things like chromatic aberration, maybe even spherical aberration, then you're going to get more reflection. So you're losing some of your light, and you can also end up getting ghost images. Because if you've got light bouncing around all over the place, well, you can start seeing things that aren't necessarily there. You can get double images and things like that. Now, modern eyepieces will use coatings on the lenses to reduce this effect. So there you've got another cost on this. How good are the coatings on your lenses in order to reduce the effect of internal reflection and scatter. So those are probably the main things that are going to affect the cost and the quality of your eyepiece. Now, the other things that you want to consider then when you're choosing an eyepiece is, well, you've got the focal length. I've already mentioned it briefly here. So the focal length of the eyepiece, which is going to be expressed in millimeters, and in combination with the focal length of the telescope, this is going to determine the magnification that you see when you look through the telescope, so the angular magnification. So if you divide the focal length of the telescope, so our objective, the focal length of the objective lens or mirror, and you divide that by the focal length of the eyepiece, that is going to give you our angular magnification. So, you know, angular magnification is pretty much, well, you know, what angle is it taking up? If you're looking at some objects like that, which is taking up, you know, however many degrees, and then you blow it up to some level where it's now, you know, that size, well, you've got a magnification in angle. You know, that's one way you can think about magnification, in terms of angle, rather than actually trying to measure as some kind of apparent size difference. So if you've got a telescope, I mean, the telescope that I use has got a focal length of the telescope of 1,000 millimeters. So if I put a 10 millimeter eyepiece in there, I'm going to get a 100 times magnification for that particular eyepiece. So, and usually I'm using eyepieces which are in this range. You know, don't typically go much outside of that range. So if I'm looking at the moon or planets, then I might go, well, I don't tend to usually go as short as 5 millimeters actually. That'd be something I might use if I'm trying to separate a binary star. You know, you just look at it in the sky, it just seems like a single star, but if you zoom in enough, you can just make out it's two stars orbiting each other. So there, you're not really caring too much about detail. You just want to see the gap. You just want to be able to resolve it into two separate objects, or maybe even more separate objects, depending on how many stars there are in the system. So there, you're trying to crank it up to the max, really, just to be able to see what's going on. If you're looking at the Orion Nebula or something like that, then go for the lower end, so that you can still make out some of the detail and you haven't just blurred it all out to nothing, because it's not bright enough to look at. So we've got that for magnification, but that's not our only consideration when we're looking at things. Do we want to magnify it or not? We want to consider our field of view. Field of view is very, very important. And there's two types of field of view. We've got the apparent field of view, and we've got the other one goes by loads of different names. Some people call it the true field of view, the actual field of view, the real field of view, telescopic field of view. There's lots of different ways of describing it. Right, so let's think about field of view in general without a telescope. So you start off, you're just looking at the world at the moment, and you've got, you know, if you're thinking how far can you see to the left and the right? Now you can't see probably 180. I doubt you can see right off 90 degrees off to either side, but you will be able to see a lot of the world. And the field of view that we've got is the angle. If you're all the way from what you can see on the far left, all the way round to the far right, or the other way round, doesn't really matter, it's the same angle. That is your field of view. Now, say you picked up a tube or something, I don't know, the inside of a toilet roll, and you decided to look through that. Well, you're not going to be able to see as far. You're going to look through the tube, you're going to see everything inside a circle, which is the other end of the tube, and then your field of view now is a smaller angle. You know, if you think, well, how far would your eye have to move if you looked at the left edge of the tube and then swung it round to the right edge of the tube? Well, you might have gone from here where you might have had 170 degrees to here where you might have, I don't know, 40 degrees. I don't know, I'm just having a guess at a number, but something smaller. So you've got a difference there in what your field of view is. Now, this complicates a little when you go look through a telescope, because we're adding magnification to the equation as well on all of this. So you've still got the size of the circle that everything is in. So that's one thing. You might have a relatively small circle, you might have a relatively large circle, and this is going to be determined by, well, your telescope and your eyepiece are going to determine these two different types of field of view, because one of them is here. This is going to be our apparent field of view, so it's our sweep from one side to the other on the size of the circle that the whole image is contained within. So this is our apparent field of view. But then you've got the issue of, well, how much of the sky is actually contained inside this circle? You know, we know if we're just looking through a toilet roll, it doesn't have any lenses on it, unless you've got weird toilet rolls. So you're just seeing the same amount of the world as, you know, your apparent field of view is exactly the same as the amount of the world you're seeing through the tube. So, but here we're magnifying things. So we've got this thing that I'm going to call the telescopic field of view. And I say I'm calling it that because I've seen people say telescopic, actual, real, true. So there's lots of different ways that people describe this field of view. And this is going to be, well, how much of the sky is actually contained inside this circle? Which is, you know, how much sky is there? So, yeah, you could have that we've got, you know, let's compare it to, let's make this our baseline case. So say we were looking at Saturn, and you've got Saturn like that, just sitting inside your field of view here, your apparent field of view. And you think, okay, well, if I took this amount of sky containing Saturn in it, so, you know, everything that's in this image, and said, well, how much sky is that? You know, it might be, I don't know, 0.2 degrees or something like that. I don't really know. I'm just, again, making a small number. It probably won't be that far off of that. But say that's the amount of sky we're actually seeing, whereas our apparent field of view might be similar to when we're looking through the toilet roll tube, that might be 40 degrees for argument's sake. So that's our apparent field of view. That's our telescopic field of view. How much sky, how much our eye has to move through. Now, it could be in this big circle that we've got Saturn being exactly the same size as it is in the little circle. So in this case, now we've got a much bigger apparent field of view because the circle's bigger. So our apparent field of view, that might be, say, 60 degrees. Our telescopic field of view is also going to be bigger because we've got more sky here. You know, the other one has only got sky covering, say, that amount. We've got all this extra sky kicking around here, all this extra angle. So we might have a telescopic field of view that might be 0.4 degrees. Something like that, let's say. Now, if we've got the, well, actually, let's change that and say that's 0.3 degrees for a reason I'm going to get back onto later on. So hold it in your mind that I've just changed that, and I'll come back to that in a minute. Now, it could be that rather than having Saturn being exactly the same size, we've got some mega Saturn in this field of view. And we've still got the same apparent field of view. That isn't changing because the circle that is all inside hasn't changed. But our telescopic field of view for this mega Saturn might be exactly the same. It might be 0.2 degrees because we've still got the same amount of sky inside the bigger circle. So it depends what it is you're describing as to what field of view you're interested in. And the way that the reason I changed this to 0.3 here is that our apparent field of view divided by the magnification is going to be our actual or our telescopic field of view. So that's why if we were going to have the same, what am I saying? The same size Saturn. So in this first case, where they were both magnified by the same amount, so the actual image of Saturn was the same size in both. Well, if you've got a an apparent field of view which is 50% greater, as we got here, we're going from 40 degrees to 60 degrees, then our telescopic field of view must also be that 50% greater in order for the magnification to be the same. So yeah, this is another equation that we've got here to relate actual and telescopic field of view. So if we've got the same telescopic field of view of this 0.2 for each one of them, then this larger apparent field of view must mean we've got greater magnification. It's the only way we can end up having the same amount of sky in a larger circle, is if it's been magnified more. So we've got this interplay here between apparent field of view and telescopic field of view, how big the circle is and how much sky is fitting inside the circle. So yeah, you need to keep those things in mind as well when you see descriptions of eyepieces and they start going on about what your field of view is. This is what matters. Right. The other thing, I think the last thing that I was going to mention with eyepieces is the eye relief. So this is how far you can position your eye away from the eyepiece. So you've got the end of the eyepiece coming out of the telescope, so the light's coming out here. You're putting your eye near it. It's nice to have a bit of a gap, so you're not getting all your eyelashes smushed up against the eyepiece, because sometimes that can appear like little spidery images. It's just more comfortable if you've got maybe a 5mm gap. You don't want to be so far back that you're just sort of hovering in space. That can make things quite uncomfortable. You don't want to be too close either. So it's nice to have some comfortable eye relief. So that's another feature of different eyepieces. Right, so let's mention, I'm going to mention two types of eyepiece. Two of the most common eyepiece designs, particularly for amateur astronomers. So you've got I've taken up a lot of this screen already, so let's put one in either corner. So you've got the orthoscopic, so that is straight seeing, orthoscopic, straight seeing. They're sometimes also called Abbe eyepieces as well, but I haven't seen that. That's after Ernst Abbe, but I don't see that very often nowadays. Orthoscopic is fairly common. They've been the most popular design for ages, although maybe they're falling slightly out of favour more recently. They give good eye relief, so that's certainly a thing. But you get a narrow field of view, so they're fine. They're good if you're in an urban area, so you're getting restricted much more to looking at the moon and planets and solar system objects, or maybe binary stars or something like that. So you're not that fussed about having a large field of view. Large field of view is great if you're looking at galaxies, nebulae, things like that. You're going to be less bothered if you're looking at the moon, maybe, again, depending on what sort of picture you want to take. Sometimes you want to have a large field of view if you're wanting to take a picture of the whole moon and you're not just looking at a crater or two. But if you're doing some lunar viewing, planetary viewing, then this is great. You get good eye relief, you get excellent image quality, but you've got that narrow field of view. They're set up with the orthoscopic design is you get this compound lens at the start. This is where the light's coming in. So you've got these two convex lenses with a concave lens in between, and then you'll get another plano-convex lens. So that's your setup. You've got 4 lenses inside the orthoscopic eyepiece. So that's quite nice. The other one, which is becoming maybe sort of usurping the orthoscopic nowadays, is the pleursal, although some people just call it plossal, pleursal. But I think that turns it into a pleursal. This is, you've got 2 sets of doublet lenses. So you've got, these were the ones that I was drawing earlier on for dealing with achromatic, with chromatic aberration. So these are your achromatic eyepieces. It's normally, the gap is going to be much smaller than that. I've kind of yeah, put those a bit further apart than they should be. I mean, sometimes they're pretty much almost touching usually with these. And here you're getting a large field of view. So you get a much larger field of view. I mean, this might be one of the reasons that they're becoming more popular. So your apparent field of view is much larger on a Plursul than it is with your orthoscopic. And your telescopic field of view is then going to depend on what magnification you've got, what your focal length of the eyepiece actually is. Now, the cheap ones, I suppose this is another reason as well. There always used to be a lot of internal reflections with these particular eyepieces, but now they're getting made so much better that the cost has come down. They used to be really, really expensive, and now they're cheaper. You've got cheaper and better coatings, better quality lenses inside these things. So I think the combination of the large field of view and how the price has dropped massively has made these ones more popular. So they're probably your two main types. But really, if you're going out and you're thinking, okay, I want to get myself a new eyepiece, these are the things to think of. You want to think of the focal length, so you know what magnification you're getting. You want to think of the field of view that you're getting. The apparent field of view is going to, how big a circle are you going to see everything within when you're looking through the telescope. The quality of your engineering of the elements in there, that's always reflected in the cost. The quality of the coatings on all of the surfaces. So yeah, there's a lot going on with eyepieces. One other thing that I'm going to slip in, it's not strictly speaking an eyepiece, but a lot of people talk about Barlow lenses. These get used quite a lot, particularly if you're wanting to ramp up your magnification, say, for looking at, again, things like planetary observing and binary stars and things like that, but also for other things. But that's usually what I use my Barlow lens for. It's a focal extender, really, for the telescope. It extends the focal length, so it's a diverging lens that you just plug in between the telescope and the eyepiece. So you put it, rather than just putting the eyepiece straight into the telescope, you put the Barlow lens in first. That increases the focal length of the telescope, so it's increasing your magnification. Then you plug the eyepiece into the Barlow lens, and then you've got this focal length extender, and it ramps up your magnification. So that can be useful in some cases. Or if you don't have an eyepiece that you particularly, you would like to be using, you can plug a Barlow lens in, and it can be seen as modifying the eyepiece that you've got available to you. So they're quite handy as well. Get a lot of use out of my one of those. So yeah, that's quite a lot there. Sort of whistle-stop tour of eyepieces and the key things to think about if you want to start looking at them in more detail.